Hey everybody, welcome back to Calculus. Now if you're watching this video, then you successfully made it through the first 2 units of our course. A unit on introducing topics such as derivatives and integrals, and then a larger unit on limits. So this is the 3rd unit of our course in which we really start to talk about the definition and theory and ideas behind the derivative. And this first video is going to talk about the definition of the derivative at a point and how we can use limits to find the exact value of an instantaneous rate of change. So on this document, just a reminder that the average rate of change formula can be found as simply f of b minus f of a divided by b minus a. It's our slope formula, the change in y, change in the outputs divided by the change in the inputs. So that can help us find the slope of a secant line or an average rate of change of a function. But what we are interested in figuring out is the instantaneous rate of change of a function, and that would be known as in calculus as the derivative of that function. So in the first unit of our course, we talked about how to approximate the instantaneous rate of change. And we would use difference quotients that involved numbers really close, or intervals small, close to 0. For example, the denominator, the difference in b and a might be something like 0.0001. And we would look at what would happen with that difference quotient as we use values that got that denominator closer and closer to 0. So that's kind of what we're going to do here today, but we're going to take it a step further. We're going to use limits to find the exact value of what a derivative is at a point. So what I have for you are really 2 examples in this video, and I'll walk you through how they work. Most importantly of all for today, in this yellow highlighted box, I have the formal definition of the derivative of a function at a given point, and we'll call that point x equals c. Now, derivative notation takes on a number of different kinds of notation. Specifically today, I'm going to use the prime notation with a little apostrophe after the function. So when you see f prime of c or f apostrophe c, that just means the derivative of f at the point x equals c. C is a number, f prime of 5, f prime of 2. But that word prime simply means the derivative. So what we want to do is find the limit as x approaches c of this difference quotient, f of x minus f of c divided by x minus c. As x gets closer and closer and closer to c, we find the denominator is approaching 0. It can never be 0, which is why this concept of a limit is so important. But that's our definition of how to find the derivative at a point. Let's apply it now to a problem. So I have a graph of a function. It's a polynomial cubic function right here. And it says to find the exact value of f prime of 4. So number 1 says to write the definition of the derivative as it applies to f at 4. So what you'll do is simply write the definition, the limit as x approaches 4 of the difference quotient f of x minus f of 4, f of x minus f of c, divided by x minus c, or in this case our c value is 4. So x minus 4. And now we're going to get creative and use some algebra to solve this limit expression and see what this becomes. F prime of 4 is equal to the limit as x approaches 4 of f of x, and that f of x is x cubed minus 4x squared minus 9x plus 46. But I'm going to do sort of 2 steps in one right here. I'm also going to evaluate f of 4 and simplify. So my entire numerator after those substitutions, skipping a couple steps here, will be x cubed minus 4x squared minus 9x plus 36. And that 36 came from me just simplifying and combining my terms with f of 4. All that is divided by x minus 4. Now, I actually can factor by grouping, and that will be a nice plan B strategy. So group accordingly, and let's see what we have here. The limit as x approaches 4 of, let's see here, x squared times x minus 4. Factor out a GCF of a negative 9 to get x minus 4. All that is divided by x minus 4. Carry with you the limit notation. and x squared minus 9. I'm just factoring by grouping in the numerator here. But that was really helpful because look now, x minus 4's can cancel, and I'm left with the limit as x approaches 4 of simply x squared minus 9. So direct substitution will now work. 4 squared is 16 minus 9 gets me to 7. That is the derivative, the exact value of the instantaneous rate of change. I might even come back here and write down that f prime of 4 is exactly equal to 7. We're not approximating here. Because I use the limit of a difference quotient, I have the exact value of the instantaneous rate of change, the exact value of the derivative. Now, what does that mean in context of the problem? Number 3 says to plot a line on the graph at 4, f of 4, and notice the slope. Remember that when we find the slope of a tangent line, we're also looking at the instantaneous rate of change. The slope of a tangent line is the derivative of the function at that point. So I drew here the point 4, f of 4, and I just sketched a line tangent to the function right there at 4, and sure enough, it looks like I'm rising 7 and running over 1. So a rise over run of 7 over 1 gives me a tangent slope of about 7, which is exactly what we found the derivative to be. So what I might say here, tell how the line confirms that the derivative is correct. The line has a slope of 7 and is tangent to the graph of f at the point x equals 4. Now problem 4 says to find the exact value of f prime of 2. Now I'm going to spare the time and the details in showing you, but I do have this note here, f prime of 2 is equal to negative 10. So by a similar process, finding the limit, we can find this to be true. But it's this question I want to look at here. How can you tell quickly that your answer is reasonable? Look at the function at x equals 2. If I were to find 2, f of 2 and observe the direction or the slope of the function at this point, here's a tangent line, it appears that I have a pretty strong negative tangent line right there. The slope is negative. Now, I don't know how strong, but if I look at this number and see that the derivative at 2 is negative 10, and I see that the function is decreasing, and the tangent line slope has a negative slope, maybe approximately negative 10, those are great ways for you to check that your answer for the derivative is something that is reasonable. Now, a side note. Here's a great activity that you can explore online or watch a video of, but it's this idea of observing secant lines through a function, but fixing one of the points. So in this case, my fixed point here on this example is 3, 2. And I just drew a rainbow collection of secant lines. And as those secant lines get closer and closer and closer to x equals 3, so from 3 to 9, 3 to 8, 3 to 7, and then 3 to 4, and so forth, 3 to 3.5, 3 to 3.1, 3 to 3.01, what's happening is that these secant lines are actually taking on the form of that tangent line to the function at that point. And that's why we're getting into this idea of the limit of the average rate of change. The average rate of change is the slope of the secant, but the limit of those average rates becomes the slope of the tangent and is the exact definition of the derivative. One word of caution, be careful with corners or cusps, C-U-S-P, cusps on graphs. Notice the tangent lines here. If I were to draw a tangent on this function from either side, look at the limits here. As I approach 3, where I have a cusp or a corner, from the left, the derivative appears to have a very positive slope. But as I approach from the right, the derivative appears to have a very negative slope. So here, these two limits, this one here being from the left, I'll just say positive, and the other one from the right being negative. There is no limit that exists right there, so g prime of 3, the derivative, also does not exist. because the limits from the left and the right side of the derivative don't match. But notice how the function is in fact continuous. So we've got to be careful with continuity and differentiability, and we'll discuss more about those topics later on. So in conclusion, I thought I would just do one final example for you to find the derivative at a point. And here's a nice quadratic, just a little bit simpler. So we'll put this one together as we close. Once again, find f prime of 5 is my problem, and I will use the exact limit definition of the derivative to find this value. So f of x minus f of 5 all divided by x minus 5. That is something crucial that we need to know for memory. We have to know the formal definition of the derivative at a point. It's that difference quotient. Now let's see here what happens when I simplify this and evaluate my limit. So as x approaches 5 of f of x squared minus 8x plus 18, and then minus f of 5 is equal to 3. The limit as x approaches 5 of x squared minus 8x plus 15 over x minus 5 is the same thing as the limit. Here's a plan B strategy. I can use factoring to evaluate this limit. So the limit as x approaches 5 of quantity x minus 5 times x minus 3, that should do it, over x minus 5. So it appears that my limit as x approaches 5 of x minus 3 will simply be a value of 2. Now what does that number 2 represent? Well, that's the derivative. That's the derivative. F prime of 5, the derivative of my function f at x equals 5 is equal to exactly 2. It's no longer an approximation. Graphically speaking, the slope of the tangent line, at x equals 2, or at x equals 5 is going to have a slope of 2. Here's a quick sketch of the function. About right there would be 5 comma f of 5, and there's my tangent line, and it certainly appears to have a positive slope. And I know from my math that the slope is exactly 2 because my derivative at x equals 5 is equal to 2. So that's the formal definition of the derivative at a point and how we would apply it in a series of examples.